Okay, great. Okay, so I'll do a recap of yesterday's stuff as well, just because
Okay, yeah.
today's lesson pretty much just expands on that, right? And we'll take it slow. Go ahead and throw out any questions that you have, and I'll do my best to answer them. Um, I think you're getting close to having a workflow that you could repeat over and over, right? So this should give you a little more structure and more to play around with. And I'll actually, after today's lesson, I'll upload a new challenge that's really more of like a lab or a walkthrough on how to repeat some of this in your own environment. Okay, so let's do a very super quick overview and let's actually pull up the lesson because I think I also found this visual from the Fullstack class that I think will be really handy. So yesterday you covered data sets and tensor data sets. Basically, tensor data sets combine your features and your labels, and you covered the training loop. Just a quick refresher. Epochs are essentially a full run through the data, and you repeat this multiple times. And the more epochs you have, the more um, runs you have to be able to kind of like amalgamate that data. Optimizers allow us to, you can think of an optimizer as like a coach or a guide. It assists with the learning, and that's through a lot of, like built-in logic and modules. So Atom, for example, the optimizer that you have been using has a lot going on under the hood that is abstracted away, so you don't have to worry about really knowing how that works. Backward step, it's another part of learning, right? So we use a different algorithm to go back sequentially through the neurons and adjust course, course correct basically in a sense. And that's about it for what was covered, right? So let's look at today's lesson. And I uploaded an image from, I thought I uploaded an image. Did I? I might have uploaded in the wrong area. Let's see, what was that image called? I am blanking on the name of that image. Let me see if I could find it and just pull it up. This is a visual that Francisco, one of the daytime instructors, created in TL Draw, and it'll kind of help us talk through some of what's happening with an actual reference. Did Omer have any visuals for you yesterday?
He kept referencing the one with like the hidden layers and then the actual layer at the end, and it showed like the little weight symbol in the
Hmm.
layers with the input and output. But that's the only visual I think he was using to get a point across.
Okay. 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 So why didn't this save? It said I added 17 minutes ago. I don't know why it's not. Anyway, we could worry about that later. For now, I think what you're referring to, Sean, is this right here, right? This middle thing.
Yeah, just that little one, yeah.
Yeah.
For like a binary model.
Okay. So let's kind of zoom out and let's go over this based on what we've talked about so far. So we start with the data, right? Down here. I don't know if you could see my cursor. I'm hovering over the bottom right box where it says pure data. This very first section, the data file, is where we start to prepare the data, right? So the data that you have might be cleaned, it might not be cleaned. And that's why we run certain things like the mean function. When we run mean, basically that allows us to fill in any gaps in the data to give us a more complete data set.
You're talking about the pre-processing, right?
Exactly, exactly. Yeah. And if I should maybe kind of zoom this out so we have access to this as well. So I can switch around between both. Right. So that would be here where we're at, right? So we import the CSV, we use fill and a, and we pass in for the first parameter the data, but with mean applied to it. So that will fill in any gaps that exist. We then drop some of this data and we assign it to a variable called features. And then we kind of call that data again as a target. What this step is, it's basically separating the features from the target, right? And the features are basically the data that we're going to use to train the LLM. And the target is what we're trying, the conclusion that we're hoping to reach. And that's why we have to separate these two things. We do a little more separation here between a training set and a testing set. And the key thing to know about this is we have to separate the data into two different parts to improve the accuracy of the response. Because if it was working off a single data set, there is more probability of it memorizing the data as opposed to truly learning to identify patterns and infer, right? Because that's what we want. We want it to be able to predict rather than just repeat what it's learned. So that's what this is. We can break it down into batches, and I guess that's going to be down here. So we're still in this bottom orange box here, right? We do a bit more after we split the data into training and test sets. We then standardize the future features. Do you all remember what standard scaler does? Can someone tell me? Yeah, I know it's like a lot of really abstract mathematical jargon. I'm not a big fan of it myself. So even looking at this like little modal that pops up to try and tell us what's going on, it says it standardizes features by removing the mean and scaling to unit variance. That's really a fancy way of saying we're going to scale everything down to the same data range, right? Because when you have data like, let's say, an age or I don't know, this is or grades, test grades, scores, basically. This data can be data that ranges from like 1 to 100, right? Sometimes though you'll have not all data will fit within this range. If we're talking about populations, for example, that that could certainly rise over 100. It could be in the thousands, in the millions. Same with, let's say, finances, right? Especially when we're talking about finances at a big organization. So standard scaler creates a unified scaling system for this. And it's a very simple scaling system where everything is scaled down to a value between -1 and 1. So that's really all it is. It's unifying the scaling for all of the data so that it's easier to work with. It's easier for the LLM to process and manipulate. So that's what we're doing here. We run some more built-in methods on our scaled data. We're really just still really preparing this data for the model. And then we convert to tensors, and tensors are really just data sets, right? So we could think of them as multi-dimensional arrays. You could have a one-dimensional, two-dimensional, three-dimensional data set, so on and so forth. And we could think about these as the raw tensors. And we only really want to make that distinguishment because next we create tensor data sets. And really, that's just combining the features and the labels into one single data set that could be, well, one single data set that exists as both a training data set and a testing data set. And then we pass that into the data loader, which is responsible for loading the data into the model. I'm not really sure how else to elaborate on that. Let's see. Um, it
I have a question.
Sure.
What is access one on the features for data manipulation?
Sure. Let's see. So when we go to this method called drop, the first argument is something that's hashable. Or no, it's a label, something that's hashable. It's so so like a table or a CSV, right? Basically data. And the access, I wish it would. I believe it's like a column in the data. So let's see if we could find some better documentation on this. So data is coming from uh, pandas processing the CSV. Let's see. Can I command click this? Axis. Nope. Axis. Let's try Google. Okay, so in the pandas data frame, axis 0 represents the rows, and axis of 1 represents the columns. So here we set the axis to 1, and that's basically, how would we visualize this?
It's the portability column, right? It's naming off the portability column and it's saying that that is a column inside that CSV file
Yeah, yeah.
based on what you just showed us. And then you have drop, so drop it.
hmm Okay, so yeah, and if you look at the CSV, which is a very long CSV, so can't even see the scroll bar. Oh, I'm going to do this, command up. That column is the very last column. It's dropping. Okay. So I don't know this CSV that well, but my interpretation here is it's dropping that column because that's our target, right? We want it to be able to assess potability. So the data that we provided right now, we want to get rid of the potability. It's kind of like giving it the answers, right? We don't want it to reach the same answers. We want to train it to reach those answers on its own. So we separate the features from the target. Great question. And that's about it for this first part. Once we've gotten into data loader, which essentially has a lot of built-in methods for efficiency and memory optimization, we can then start working with that data inside of our model. So let's go back to our image. Here we see when we're passing it to the data loader, we have a data set with both the labels and the features. So this is the tensor data set. And I believe this is what we're going to be covering or recapping next as we talk about the model. So we have these uh, these layers defined here, right? And if we look at what's being passed into these linear layers, These are the number of neurons that we pass in or instantiate. And originally in this image, we would have been starting with something more like this. So self dot linear equals nn dot linear. Looks like there was three. So think of these as just being input outputs, right? So for this first linear layer, we are inputting three um, nodes of data, and we want to simplify this down to two nodes of data. So now we, well, what's happening in between that step, like during this step, is now the model is assessing the relationships between these different data sets, right? And it's using things like uh, weights, which are essentially biases, internal biases, to help it reach a probability, an answer, right? And we can, today we're going to be talking about optimization. So we're going to be talking about how if we increase the number of inputs, and then increase the number of outputs, this will give us more wiggle room to play around with. Um, but before we get there, still recapping here, at each layer, we want to be able to accept the same number of inputs as the outputs in the previous layer, right? So here we have self.linear2 being layer 2 equals, sorry, what was that?
Um, when you were saying nodes, so when you're referring to like on linear one, that value of three, are you saying that those are three nodes?
They're they're neurons, right? And so
Okay, hold on. Just before you keep going, the reason why I asked that because my initial thinking was that when we were working on this, that initial value, what we are passing into it, I mean, the tensor that data, it has the elements in that object in that list have to match that same initial value. And
mhm.
so
Like
the
in our, yeah, like in our potability,
neurons,
yeah, there's like 10 columns, is what I thought. And
yeah,
then we dropped one, so now there's nine, so we have to start off with nine. That's what I thought too. Is that kind of what you were saying too, Mike?
yeah, that the elements in a sense are the neurons.
Mhm.
That's
Yeah, no, exactly. That's how you like determine the number of that's the input, right? So the data that we're first inputting into the model, we're passing it in as nine. But we could also essentially like instantiate like additional neurons within the model. And in this original example, in the image, the data set has three, it's a 3 by 3 matrix, right? So that's why this example starts out with three. We would be writing that out like this. And then we're then sequencing it down to two as an output, which then gets passed to the next layer, all until it reaches the activation layer, the sigmoid, where the sigmoid function will finally create an output between 0 and 1. So it's like just layers and layers of number crunching, right? So yes, to your point, Mike, it's the input from the data set. And yes, to your point, Sean, because we're working with the potability CSV, which has 9 columns, that's why we start off with 9 here. So we could then visualize this. If this was for the potability CSV, there would be 9 of these neurons in that first layer. But instead of just creating two neurons, it's going to be expanding into 20. And that allows for more connections between the different um, chunks of data, right? And that's going to allow the model just a wider range of results that it could then crunch down later on. And I know this is like super hard to conceptualize, but if we look at, if we run this right now, or before we run it, let's actually first get rid of this because that's no longer relevant. And then let's maybe do something like this. I'm sorry.
Julie,
Yeah.
why would we want to increase the number of neurons if we already pass in the amount of the data? I can understand the reduction, but to increase it, what more associations is it making if we're not telling it what associations need to be made? You're just making extra data points that are out there, but what how is that beneficial, I guess, adding more neurons if we don't have that many to start with?
Yeah, that's a really great question. And I'm not sure I could do the explanation justice because I've been trying to kind of explain it as creating more of these cross connections, right? But let's first run this and see what's happening. So I've kind of adjusted what's happening here. I modified the layers. So instead of going up to 20, we're just crunching down to smaller numbers until we have a single output that we pass to the sigmoid function. And if we run this, we have an accuracy of 0.39. Now, oh wait, no, that's old data, I think. Let me just make sure all of this is cleared out. I'm gonna restart. Oh wait, that should have been, that's just an empty box. That's an empty box. Okay. So shoot, what just happened. Okay, here's where we're at. I'm gonna run it. And did I actually see a few times? I don't think I did anything. Okay, so we ran this and where's the, I'm missing this. So let's, okay, I might have to run this sample. No, I should be able to skip all this. Okay. Right, in line 18, I'm having some kind of issue. And that is, what's going on here? Object has no name. Oh, I see. Linear 5 doesn't exist. Okay. So, right. We're trying to pass linear 5 to forward down here and it doesn't exist. So that's why it's throwing an error. So maybe what I could do is comment that out and pass in 4 instead. And now let's run this. Now let's rerun this. So now we're going to that training stage. We're going to be running through some epochs. Let's just do one epoch. And We have an accuracy of 0.37. Okay, so that's our accuracy. Now, if we expand this back to what it originally was, and this will have to go back to being 5. Let's rerun this. Wait for our green check mark. Run it through the model again. We have an improved accuracy. So to your question, Mike, why is that happening? How are we improving the accuracy by increasing the number of neurons? There's not a simple way to answer this. I think about it like think about your brain and like how
From
your
what I read, not sorry to interrupt, but from what I read, it's increasing the complexity of the learning, right?
Mhm.
The more it can learn it, the more complex patterns it can learn by increasing the amount of neurons it can learn from. But there's
Exactly.
some drawbacks to that too.
Yeah, yeah. Some drawbacks would be like additional processing time, right? And when we're working with additional data, there's going to be like the higher and higher chance of overfitting the more that we run through something. And that's why we're going to run through some optimization methods to help prevent that.
Can
But
you
my,
explain overfitting?
yeah, yeah, we'll talk about it a bit more. Broadly, overfitting is kind of like skewing the data, right? So it's kind of like asking a bad question, a question that's like so loaded with, you know, words and conditions and stuff. Like think about like when a journalist is asking a very loaded question. They're trying to guide a specific answer out of somebody, right? That's overfitting in a sense. By providing too much information, you're guiding the AI as opposed to allowing it to reach its natural or a more accurate conclusion.
So it's memorizing versus learning.
Yes, that's one cause for overfitting.
Thank you.
Mhm. And Mike, does that help? Uh, does Sean's contribution answer help you visualize the layers a little better?
It does help me to visualize. I mean, there is some stuff that's going on definitely underneath the hood that I want to look into because it's that's very interesting that by adding extra space, let's just say whatever it's doing, its accuracy becomes better when it already has the initial data points. The only thing that I could see by having that extra space, it allows it to take more guesses, maybe if that's what it's doing. I don't know, um but the true statement is that by adding more, it's able to learn more per se. Um, but yeah,
Yeah.
thank you.
Okay.
Do you have a representation of what one neuron looks like? Is it the input? Like one neuron is that input? Like
Yeah.
that's where I'm kind of getting. I guess I don't have that puzzle piece for learning.
Yeah. You could think of it as being that input with um, additional, just additional data, right? Because like the weight is the data. It's a bias that basically has been um, created by the model and associated with that value to give it a measurement of um, accuracy that helps it calculate the answer that it's trying to predict. A lot of this, the thing is, a lot of this comes from like, let's say, optimization theory, right? So I don't really know the nuanced mathematics behind it all, but yes,
Alrighty.
to your question, Sean, yes, like that is an input. That is the input with more layers. added to it, right? It's kind of like when you learn something, you associate it with other things that you know, right? You associate its accuracy, you associate something's validity, you associate how much you like or dislike something, right? So you could think about what's in these layers, these neurons, as being the amalgamation of all of that. Okay. So if I was actually using T-Ultra, I'd be able to expand and add more nodes, and you'd be able to see that we have more connections, more intricate connections and whatnot. So this is the best we have at the moment in terms of visualizations. Not quite sure how to interpret these later ones. Here, I think what we could consider here is every time it's going through an epoch and running its calculations, right? It's also running some additional methods. First, it's using the optimizer to apply this zero gradient function, resets the gradients of all optimized tensors. This will have lower memory footprint and can modestly improve performance, but it will also adjust certain behaviors. Okay, what's next? We also calculate loss, and we use that using this criterion algorithm. I forget what BCE loss stands for. It's just another algorithm. And this essentially calculates the loss of certainty, right? So as it's going through an epoch and it's coming around to like spitting out a conclusion, it's also measuring how confident am I in this conclusion. And ideally, we want to see this loss number decrease because that's letting us know that we are becoming more and more confident in our answer. And that's where this backwards regression comes into play, right? This basically allows, yeah, this back propagation. Shoot, let's keep doing that. This back propagation step is what goes back through each neuron one by one, layer by layer, and it course corrects. It slightly adjusts biases and weights inside of that neuron based on what it's learned to improve its answer on the next epoch. And it's just going to continue to do this and optimize until finally it's run through the number of epochs you've specified and it goes to evaluate. And when it goes to evaluate, it will pass it on to some sort of evaluation method. In this case, did we specify that earlier? Yes, we specified sigmoid here. And so at the end of each epoch, it's going to this sigmoid function, which essentially just reduces everything to a number between 0 and 1, right? And that is a representation of the accuracy of its prediction. Okay, that is our recap. Where's everyone at?
I have a question.
Sure.
What, will you scroll up
Yeah.
and go to your layers?
Hmm.
What, I don't know if you mentioned it. I don't know if it is considered optimization theory or not, because I had heard when you said that, but how do we determine the number of neurons that we want, right? I'm especially from initially we already know based off the columns. And
Hmm.
that is a starting point, all right? But how do we decide I want to go more? And if I'm going more, where's a good starting point at? Or if I just want to go less, how much less? I had saw that initially that, 3 layers is enough for a certain, but of course, there's always more, right? What what would I need to read on? Uh,
In terms of application theory, I don't know exactly what what principles to read on at this part of the flow to help you with that. Um, this and a lot of this can really be learned through experience and repetition and just playing around with it because the number of values that you output and input, there aren't a lot of hard rules that you have to follow. The only real hard rules is the input has to match the output of the previous layer. And Francisco, who wrote all of this material, he he just found a method that works for him. He didn't really give deep explanation of why it works for him. He said it just came through his own experimentation. And so what he does is he'll work in multiples of three. So I know 9 times 3 isn't 20. That was the example that he gave. Um, and 20 is like, or 15 is like what, 3/4 of 20. So he'll kind of like just play around with multiples of 2, 3, and 4. And that's what works for him, is what he said.
okay, I mean it's just something that I wonder because I would think that the process would be different if we're training a model to evaluate images versus to evaluate something moving versus
Mhm.
evaluate math and calculations, right?
Mhm.
I would think that there's something that it would be different or more just, but okay.
Yeah. Yeah. There may be. I'm not sure how to reach that conclusion. Um,
Okay.
so for the time being, I think just finding a pattern that works for you is a very good starting point because this isn't going to be the only area that you can tweak in order to adjust the response, right? We saw that giving additional neurons does give us more accuracy. We were able to jump the accuracy up from 0.37 to 0.628, but there are also other ways to do that. So the three ways that we're going to be covering today are uh, what is it? ReLU, dropout, and early stopping. ReLU is just another function. It's rectified linear units. And let's go back to, oh yeah, okay. I remember now. Yeah, let's go back to today's README to see what that looks like. So rectified linear unit is a popular activation function that can help improve model performance. So unlike sigmoid, it does not saturate for positive input values, allowing models to converge faster. That's one way to put it. One thing that slows down the sigmoid function or tanh is remember how earlier we talked about standardization, scaling these values to being something between -1 and 1. With negative values, there occurs this issue, I think that's called the vanishing gradient problem, that happens through activation functions like sigmoid, um, because I can't I don't think I could very succinctly explain, but it's how those negative values affect like the entire calculation, right? I guess an analogy would be if you have water flowing down a pipe, like that's a positive value, right? Does it make sense to really measure water flowing in the opposite direction? I don't know. These are just different activation methods, right? You can play around with which one you want to use based on your use case. What we're going to see though that in this simple use case by using ReLU, we can improve the accuracy. And really, we're just getting rid of negative values. That's what this, I believe, is trying to say here, that it does not saturate for positive input values. And by replacing the sigmoid function with ReLU, we can potentially enhance its ability to learn complex patterns. Again, keyword being potentially. We're showing you different activation methods, different things that you could tweak when building an LLM. And in a real world application, it's going to be very contextual, right? It's going to, what you use is going to base on your use case, on your data, and probably some experimentation with that data. Okay, or those different approaches. Okay, so there's also dropout, which is another technique we could use to improve accuracy. And this is one that helps to prevent overfitting. And I think a good analogy for this is, well, before we go into the analogy, let's go back to this image and let's look at these neurons. So what dropout does is for each epoch, it's going to temporarily deactivate. Oh, why does it keep doing that? It's going to temporarily deactivate one of these neurons. This way, as it's running through over and over again, it's not over relying on a particular neuron, or it's reducing the probability of over relying on any individual neuron. So, like, let's say during one epoch, this purple one gets deactivated. Now, only the red and yellow one will be utilized. Next run, maybe the red one gets deactivated. Okay, so why do we do that? Let's think about let's think about having employees. You're running a shop or a business or whatever. You have a team. You're not going to give all of your hours to like one or two select employees, right? You're going to distribute those hours evenly. You don't want anyone to burn out from working like 5 times as much as anybody else. Not only that, I mean, like people have different learning styles, right? So if you're always giving like the same assignments to the same person, you're limiting the results to one particular perspective or viewpoint, right? And that's essentially what's happening here. By utilizing dropout, we can more so randomize the flow of these inputs through these various layers and calculations, okay? And that's essentially called fluidity. We're creating fluidity by creating more randomness in how this data flows, right? And I believe that's what this little these little charts are trying to articulate. Instead of, like a linear path left to right, we're really just kind of like zigzagging around all over the place, right? But we want that because the more that we want that, or the more variety we have, as we average the results or find like the the average of it all, that will give us ideally like an optimized answer, right? So that's dropout. It basically deactivates certain nodes per run. So that's another way of preventing overfitting. Overfitting again like being too reliant on certain data or like memorizing certain data as opposed to inferring. And finally, there is early stopping. So this also can help prevent overfitting. And really, you could think about this as just not overloading a response with like too much information, right? It's or kind of like what's happening now. I could keep on trying to explain these concepts to you over and over and over again, but what's going to happen? You're all going to check out because I've just been talking for hours. So ideally, I should stop at some point and give you all a chance to process that data, right? In a sense, that's what early stopping is here as well. We don't want to just continue running these calculations over and over and over, especially if we set like a high number of epochs, which is one way to improve accuracy, but it's more memory intensive, less performant because it requires more power. So we want to stop at a certain point. Now, what's the logic behind that? The way an early stopping method could work is we will identify loss. So earlier we were identifying loss, but now we're also creating this variable called patience, right? And patience is essentially identifying when validation loss stops improving. So we're really waiting for, as we're identifying the amount of loss that happens, we we can stop once we stop seeing like a change in that number. So like let's say the first few runs we see a big spike, the loss going down from like zero point 0.6 to zero point 0.4 and from zero point 0.4 to zero point 0.3. If eventually it's just kind of hovering around the same number, an early stopping method can cut it there as it's identified that there's no real value, additional value in continuing. Let's see if, I wonder if one of these, yes, this later example should show that. Yes, okay. So far, we've been able to reach an accuracy of 0.62 by increasing the number of nodes we worked with. Let's throw early stopping into the mix. So let's take all of this. Let's run it. Okay, see how during every epoch we have variation in the loss that's assessed. And maybe that's not a great number. Let's increase the number of epochs to like, let's say maybe 1,000. And let's adjust our print statements. I don't know, let's just leave it at that. Right now it's going to be checking for every 10, 20 values, maybe we try 10. All right. So we're seeing that there's not a lot of variation in the loss, right? So before we go any further, it just stops. We're not reaching 500 epochs. It's identified through its patience that there's no point in going further. And now if we rerun for accuracy, we've got a 0.628, which is not really, yeah, no, it's not higher at all. It's the same number, I think. Okay, so in this case, it doesn't seem like the early stopping has had much of an impact. Oh, but I also changed the wrong method. This is from a previous, yeah, it basically just reverted back to 500 from 1,000, but regardless, we didn't even reach that 500. Um, Let me just make sure that it's actually evaluating the right model. Okay, so it's still, Okay. Right. So yeah, up here we were running with 1,000 epochs. No, this is what I changed and didn't actually run, I think. I just want to see like if I missed a step or something that would have led to a different result. But while we wait for this, where's everyone at? How's everyone feeling about optimization so far? Not great.
Um, that when you were discussing about the Riku, I think it was called.
Oh, the ReLU?
Yes, the Ralu, and it removes a node, I think you said, or a neuron.
Yeah, it doesn't remove it. It just temporarily deactivates it. So
So,
it's going to be inside that layer.
so we're passing in the data. Each of the elements is a node, is a neuron. So if it takes out a neuron, it's removing a data point or that piece of data.
Yeah, it well, it's not removing it again. It's just deactivating it, so it's not being calculated. It's not being
That's
considered calculation.
that's okay. It's okay. It's just ignoring it
Yeah.
or whatever. Even I don't, and this may be going down a rabbit hole, but I don't understand how it can come to accuracy by removing, well, not removing, but by um, ignoring a piece of data that it needs.
Well, put it this way. We're working with large data sets, right? So again, we know that for each layer, this first value that we're putting in, we're saying nine columns. Wait, this is the wrong CSV. 9 columns. That's still a lot of rows inside that, right? We don't want it to just run through everything over and over and over again, right? Because there's not going to be any variation. Every time it runs through these activation layers, it's a different row that's getting passed in, right? We want to reduce the chance of that same row being used over and over, right? And we could do that by using ReLU. So one pass through, it might select row 528, and another pass through, it's not going to because ReLU has randomly selected that row to be deactivated.
Okay, now that makes sense. Okay, at first, the way that I was thinking, it was ignoring like that whole column of data. I'm like, wait a minute, that doesn't make sense. Okay, but in other words, it is ignoring the rows across all the columns of the. Okay, got you. That makes sense.
Okay.
Thank you.
Okay. And let's see, let's go back a bit further. Where were we? Oh, right. Inside of here, we were, yeah, let's go through ReLU and optimization one more time, and let's actually do it through code. Okay. So I'm just going to get rid of this because we don't need that now. Why is it not letting me? Now my VS Code acting up. It's not letting me edit this. Oh, there we go. All right. I think it's time for a new computer, but that'll be a tomorrow problem. Okay. So 4. Okay. All right. Let's first talk about dropout. And when we talked about, well, let me also like just double check in my head what's going on here. We talked about dropout. Yeah, what you and I just talked about, Mike, I think we were actually talking about dropout as the deactivation. So yeah, about these nodes getting deactivated, that's dropout. And relu is the function that removes negative values. And I guess the analogy for that one is basically, I don't know. I mean, I don't even know if the flowing water thing is a very great analogy. Um, but it does help to prevent certain problems that other functions run into, right? And again, an example of that would be the vanishing gradient problem. The way the sigmoid function processes these numbers because of the inclusion of negative values, it's got a wider range of data to consider for one, and the negative values will impact the calculations in a different way than a positive value will, right? So ReLU essentially just kind of shuts out negative values, and it does through this very pretty looking mathematical function that I'm not even going to try to break down. And what we do want to know is how to use it, right? So first, let's go over how we would implement dropout. We would, is that, let me just double check something. Okay, let me see. Let me see today's README if that's even in there actually. Shoot, it's not. Okay. Okay. I'm gonna grab all of these values and I'm gonna duplicate it with I need and think of a fast way to do this. Sorry. Okay. Guess that's better than nothing. So it's going to be DP for drop. And we're going to replace the function that we're calling in here, right? So instead of using linear, we're going to use dropout. Shoot, I think this is not sure this is gonna. Okay, then let's look up the dropout function. And okay, so that P is probability. Right, that's what it was. Okay, so for each layer, we could specify probability of dropout. And so we're not passing in these values. We're passing in instead a probability. So let's just do 0.5, 0.5 for all of these. Good. And now we have to adjust these so that they utilize that. And basically, we are going to take all of these linear values and we're going to wrap them inside of these dropouts. So basically, this dropout function is going to be called on every linear layer. And there's going to be a 50% probability of this layer being deactivated. So it's going to look something like this. And again, let's see what's the fastest way to do this. That's self.dp, colon, or parentheses, 2, 3, 4, and I'm going to need one more for 5. Okay, so let's save. Let's now run this. Make sure it doesn't error out. Okay, we're good. And now let's run through training again. Okay, we have an issue. Okay, did we change did we change anything else? 25. Oh, I think we shouldn't, we're not supposed to call it on this last, right? This last layer can't be, yeah, that wouldn't make any sense, right? Let's go back to this image. It would not make any sense to deactivate this last layer, right? Because if we deactivated this last output, we can't reach the sigmoid layer, the activation layer. So yeah, I'm going to delete DP4, or sorry, DP5, because we're not supposed to have that. And let's save. Let's rerun. Let's rerun this. Okay, so I hope that error kind of helps to visualize this, right? So basically every dropout function that we're calling, we're instantiating this dropout class to call it on every linear layer. And so within every linear layer, there's a probability that certain nodes are going to be deactivated. We don't want to do that on this last output because we need that last output. We need at least one output to go to the sigmoid to finally be crunched down to a value between 0 and 1. So that's taken a while, probably because we have such a high number of epochs. Probably should have lowered this. So this is why we want early stopping. I probably shouldn't have ran this one. Just going to minimize this. Okay, so it's taking way too long. I'm going to see if it lets me run. Oh, okay, it finished. 0.628. What did we have before? Still the same data so far. Like, that's kind of really weird. I'm going to save. I'm going to restart. Just want to make sure that we don't have like any cache data or anything that's messing this up. So let's rerun this. And instead of running this one, we're going to run the one with the early stop. Okay, so we saw big jumps in the loss between these first several epochs, and then by the end, it was just hovering around 0.58. And now we could run through a check for the accuracy one last time. Oh, and it's still giving us that 0.628. But again, sorry, it's just bugging me that it keeps spitting that out. Like something's got to be wrong. Or it's just keep giving the same value because there should be variation even in this early step, right? So I commented all that out for some reason. Here we're going to train without early stopping. Actually, no, we do want early stopping. Or I'll just do a low number of epochs so we don't need early stopping. All right, low number of epochs, 0.37. Increase our number of epochs and add early stopping. Stops a little further than before. And man, why does this last one keep giving 0.628? There's got to be something wrong with the code down here. And accuracy. Where's the item coming from? And so it just keeps going back to 628. Okay. I was hoping for more variation in the numbers. Might be something wrong with my code somewhere. But we do see that we can increase accuracy by increasing the number of epochs, um, early stopping, utilizing dropout. And let's also just throw in ReLU into the mix. ReLU is basically, again, the function that's going to remove negative values. And this one's pretty easy to implement as well. We can wrap this in some parentheses so we could call the ReLU function on it. We're going to call it from this functional class, which we're just importing through Torch. And let's just go ahead and call it on all of these. Okay. All right, now let's save. Let's restart again. Let's clear all outputs and let's run. Okay, that's done. I'm gonna utilize early stopping. taking a lot longer before it stops. We're gonna finally let me just double check something. Go back to I'm gonna okay, instead of like holding up the class, I'm gonna tweak this a little more, see if I'm missing something somewhere, or if for whatever reason it's just gonna keep spitting out 0.628. Okay, how is everyone feeling? Did at least optimization make sense through early stopping, dropouts, and ReLU?
I got lost on the early stopping. I don't know how you implemented that.
Okay, yeah, let's go back to the early stopping.
So you had to make a whole new class called early
Mhm.
stopping.
Yeah,
And is that just a copy and paste of like the actual class itself, or did you have to build all that?
let's see. I think,
Because it's not in the repo, so I'm like confused as to what's going on here now.
yeah, this I grabbed this from Francisco's lesson. So let's see what the example is in the repo. A basic implementation is we're defining our best loss. It's just going to be a float. So in here, we start off with a default value of none for best loss because this value is going to be identified by the when this method is called, right? So then we set a patience counter to 0. That's going to count its patience, which is basically once it reaches that point where it's kind of like um, yielding the same value, that counter is going to go up. Once it meets this value that we set, then it's going to stop. So let's go back to our example, and we see that it starts to stop. It stops at 189. And why did it stop at 189? We set our patience to, oh, there it is, 5. So let's see. If the self that counter is greater than or equal to patience, then we set early stop to true. Otherwise, the counter is set to 0, and we update value loss or the best loss value. So every time this runs through an epoch, it's calculating the value loss, right? And it's going to identify if this current value loss is better or worse than the one before. And then it's going to increase the counter. So here it's checking, it's comparing the current value loss to the previous loss. And we're only logging every 20 runs, so we don't have a very exact look as to why it stopped 9 instances later, but we could infer that for the last 5 runs, for the last 5 epochs, it was not seeing enough of a change in the value loss. and that's what triggered the stop. Okay, and if we compare to the example in the README, value loss equals the compute validation loss. I don't even know where that comes from here.
See, that's why I'm confused. Like you got stuff from another instructor that wrote this, I'm assuming, right?
Yeah.
And he's got this little block of code here for the repo. I'm
Mhm.
like, okay, well, where does this block of code fit in the for loop for the epoch? Does it come after the optimizer step, which is code that we have from the previous courses of instruction here?
It's okay.
Like what is that? Is that is that something that we were supposed to have created, compute validation loss, or is that inherent to a library? Like that's where, once again, where this lecture is failing.
Yeah, I'm sorry. I don't know.
Well, it's not your fault. It's whoever made it. There's missing puzzle pieces here. Like I understand this is supposed to calculate at a certain point, and then it just stops it.
Mhm.
But I just where do you put this block of code to make it work and make it help us understand like how it's working, you know?
Yeah. Yeah, I have no answer for compute validation loss. What I can do is I can share all of this. I'll update the README to have the other instructors. It's basically the content from like the Fullstack um, class. So let me see. We go to
Like where does your training code stop? Does it like in that for loop? Does it do the training code portion first and then it gets into uh the the loss section, like calculating the loss or early stopping? There we go.
yeah, I'm going to presume that compute validation loss is going to be part of the training code.
Because it's I mean it says training code here, so it's like training code, which I'm in my head, I'm assuming that's everything we've been using in the previous lectures, like with Umar yesterday and everything.
Mhm.
That's my assumptions, though. I don't know if that's correct.
Yeah, I mean, yeah, when I looked through this, it seemed very bare bones to me. So that's why I referred to Francisco's lesson from the daytime course. And I could provide that again in the README. So let's see. Go to full stack. Let's go over to AILMs. And today's, shoot, what? I think this is Francisco's, or maybe it's Adam. I guess Adam made the last change. Oh, yeah, okay. Okay. So I don't know why they're not providing that code. I remember now. I actually got it from the curriculum notes repository. Here we go. X-ray demos and notes. Yeah, the daytime class, I guess they have a notes repository where they add content as they go through the curriculum. And the notes for optimization is basically, I think, what Francisco goes through during the actual class. So their README doesn't provide this either for whatever reason, but I can include it in our README. I don't see the harm in doing that. So yeah, in this example, we were seeing like what we saw in my terminal. It's running through the early stopping and basically that is utilizing that same training code, right? So here we see the training code, which is setting a number of epochs, and then it's iterating through those epochs. It's down here again, but with the addition of validation or value loss calculation. So yeah, it's just adding to the previous code. Why there's no explanation is beyond me. I'm guessing it was just written this way because Francisco knew that he was going to write it out during class through the Jupyter notebook. That's my guess.
Well, for
So
your guys' class, it would be nice if it was in there.
yeah, yeah, I agree. I do agree. So I'll,
Yeah.
I'll throw it in there. Okay, so that's optimization. If you have questions, Slack them or ask them throughout the rest of the day. We've been here for a while, so let's take a break. Um, During that break, I am going to update the README. I am going to write a quick lab so you could follow through these same steps and play around with a different data set. Sound good?
Sure. Sounds good.
Cool. Right.